So again, let's review the causal hypothesis, the one-tailed test. So the hypothesis, for example, might be employee training programs will reduce absenteeism. So that reduce tells us it's a one-tailed directional test. Employee training programs, that's our IV, it will reduce, that's our directional. Employee absenteeism, that's our DV. So again, we're basically asking the question, does an independent variable, in this case getting employee training or not, have an effect on employee absenteeism, a behavior? And if it does, that would give us strong evidence that we may want to continue to invest in employee training programs. If the purpose of employee training programs, however, is solely to reduce employee absenteeism and the null hypothesis supported, we don't find that effect, that'd be a strong evidence that we may be wasting our money on this particular intervention. Now again, we have a specific hypothesis with an IV, a relationship, and a DV, which means that though we're not going to write it out, there is a null hypothesis, that there will be no change or there will be more absentee as a result of the training. In other words, it's mutually exclusive. Any other possibility is covered by the null hypothesis. So our alternative hypothesis is that there'll be less absenteeism as a result of training. It's a one-tailed hypothesis. So basically we're looking at a reduction. So if there is no change or an increase, both of those results would support the null hypothesis, while we only support the alternative hypothesis if we find specifically that reduction or less absenteeism. So again, just kind of thinking it through mathematically, when we're looking at the test statistic probability distribution, remember this is not actually a normal distribution of the scores of your sample. This is a distribution of potential results that you could find in your study based on your sample size. In other words, we're basically saying, what is the potential possibility of any one score coming out of your actual test equation when you calculate it, so your test score, compared to all possible test scores? And as a normal distribution, higher scores and lower scores are going to be less and less likely. So the higher we get or the lower we get, the less likely those scores are going to be. And most of the time, statistically speaking, the average is going to be there isn't going to be an effect. So we're basically looking at the frequency or likelihood of any one test score coming out of an equation. And if the chance of that happening by random chance is less than 5%, that's when we're going to claim critical statistical significance. So again, with a one-tailed test, we're looking at a specific direction of improvement, which means that 5% is all on one end of that distribution, and that's where we get that little bit of extra power from. So basically, that sets our critical value. Any score above this value means that that score appears in the distribution of possible scores less than 5% of the time. Therefore, we are 95% or higher sure that that effect was not due to chance. It was due to a meaningful difference. Everything else is we don't reject the null hypothesis. There is no relationship or effect. So 5% of the time we claim an effect. Anything else, we don't claim an effect with a directional hypothesis. And again, with that 5%, we reject the null hypothesis. We'd support the alternative hypothesis. There would be a relationship. Now, with a two-tailed test, we now have a hypothesis. Our new drug treatment will cause a difference in depression. So notice here again, we have an independent variable, a drug treatment. In this case, probably you get the drug treatment or you get a placebo. We have an effect. It will cause a difference. So we're claiming in our hypothesis what we're expecting. We're not expecting a directional hypothesis then. We're just expecting some change. And we have our DV, depression. So again, if we found support for this, if the drug treatment increased depression, that would tell us something about the drug. We might be actually testing side effects. In other words, the drug might not even be meant to be dealing with depression, but we're checking to see, does it also affect depression? Is there a side effect? Or we may be testing a new drug that we don't know if it's going to work on depression, but we're wondering, hey, maybe it has an alternative use. Maybe it reduces depression. So there's a couple of things we're looking for in one study here, which is why we've gone with a two-tailed non-directional hypothesis. Again, our null hypothesis has to be mutually exclusive, and it has to be exhaustive. So it's going to be, there is no change, no positive or negative. So basically our alternative hypothesis is a two-tailed hypothesis. There's simply going to be a change. And our null hypothesis in this case is in the middle, just no change. But remember that in order for us to claim statistical significance, we have to be in a very small number of scores. And that's where this changes kind of the dynamic. So in this case, we still have to have that 95% chance that we support the null hypothesis. In other words, if we don't find a strong enough effect, we're simply going to say we don't have statistical significance, the null hypothesis is supported. And we still only have 5% of this distribution that we can devote to actually finding an effect. So in this case, we have to split it to both above and below, high and low. So we now need a critical value that's actually plus or minus 2.5% of all values at the top and bottom of the distribution. So in this case, again, we have a 95% chance in the middle of not rejecting the null hypothesis and basically saying our alternative hypothesis, when it's not supported, we have supported the null hypothesis. And we still have a 5% chance of claiming an effect. It's now just split between the both directions, either higher or lower. And this is where you sort of lose power. The value you now have to find when you run that critical value is higher than if you had a one-tailed test, but you'll also be able to claim statistical significance if you find a strong increase or a strong decrease based on your hypothesis. So I'm hoping this helps you connect why the statement of the hypothesis matters as we move forward to our statistical analysis, specifically whether it's a directional or non-directional test based on how likely it is you're going to find the effect. So again, when we talk about a test statistic probability of distribution, what we're always really comparing for, what those tables are showing, is kind of this normal distribution. And again, what we're wanting is basically what's the chance of 5% or less of the population being above that value. If we're putting it into z-scores, that critical value for a directional test is 1.645. In other words, you need a z-score of 1.645 on this distribution or higher to know that you're above 95% of the possible scores. So basically what we're looking at is that our sample distribution, the mean that we calculate from that sample distribution, that score, actually lies above that critical value. Now recognize that this is an estimate, that our probability distribution and our sample distribution, we're basically looking at static values in variables, which means that there's always a chance we're wrong. There's always a chance that we claim statistical significance at an alpha of 0.05, saying our p-value is less than 0.05, and actually it was still due to chance. It's just very unlikely. So the probability of distribution of the population is a measure of probability of probable effect sizes, with the mean representing no effect. Lower values, a stronger and stronger, less and less likely due to chance. Negative effects, a higher values of higher and higher positive effects. So again, if we actually have a test statistic that basically is in the middle of the probability distribution, that means it's not significant. It's a null effect. And as it gets larger and larger, either positive or negative, the chances of it actually being due to chance becomes less and less. So just as your sample mean effects have a value and an estimate of confidence around them, that value, so does the population probability distribution. So what we mean here by your sample mean has a value and an estimate of confidence around that value. The estimate of confidence is is basically your standard deviation. So whenever we report a mean, we also report how many scores kind of varied around that mean. Were people widely varied around that score, or were they tightly varied around that score? And likewise, when we're looking at the probability distribution for calculating whether something's statistically significant, there is also confidence around that. In other words, each score is static. If I report that you need a 1.625, that's a static score. But there's error around that as well. These are all just estimates. And that's why we never report a p-value equal to 0. We always report, at worst, equal to 0.001. We're basically acknowledging the fact that this is an estimate, and there's always a chance that no matter how strong the effect was, that maybe it really was just this one particular sample, just happened to vary very strongly, and you wouldn't be able to find it again. So your sample's distribution of estimate of effect size, the larger the variance, the less sure you are of the actual value, and the less variance, the more sure you are of the value. This is one of the reasons why we become more and more confident of claiming an effect with a larger and larger sample size. As that sample size becomes larger and larger, we can trust the value that we found within it and the test statistic value more and more. It's more and more likely to be representational of the actual value of the population, and therefore a smaller difference can be assumed to be statistically significant. The smaller the n, the smaller our sample size, the more likely it is that we did just pick up some random variance. We just happened to get a group that differed. And even if we claim statistical significance, we usually need a much larger value on that test to be able to make that claim. So one of the ways we can kind of conceptualize this, and this is the first really new idea in this particular lecture, is the standard error of the mean. It's the difference between the sample mean, a known effect, and the error variance of the population mean, which is estimate. So this is basically a standard measure of the distance or difference between the sample mean and the population mean. In other words, this is another way to conceptualize whether or not you found a meaningful difference in your group. This isn't p-value. This is kind of giving you an idea of how much error there is in your p-value. So this is another way to kind of conceptualize testing whether or not we have a meaningful difference. So the expected value of a mean, obtained sample effect mean, is compared to the estimate of the possible population effects means. So remember, our probability distribution is a probability chart of how likely any one particular mean would occur in the population. So we're going to refer to this as mu, that little symbol with the U with the tail. And what we're wanting to actually calculate is beyond p-value, what is the standard error of our mean? And the way we calculate this is actually we take the value of the actual mean, or basically the standard deviation of that mean, and then we take the square root of the n. And that gives us our standard deviation of distributions of estimated mean samples. Standard difference between the mean and the mu. How wide is the variance in the estimated population effects means? So again, sigma m decreases as sample size goes up and decreases as error also goes down. So again, what we're going to be calculating here is we're going to take the standard deviation of our mean, we're going to divide it by the square root of our n. That is going to be the standard deviation between the score that we got in our sample and the score in general for a null hypothesis, the middle of the probability distribution. Now, this is kind of an esoteric concept, but generally speaking, the larger this is, the more we can trust what we found. So in the simplest of terms, the larger your effect, the more likely it'll be found to be significant. And the larger your sample size, the more confident you can be of your estimate of effect size in your sample is accurate. In other words, it contains less error. Now again, generally speaking, we're comparing means, and we do definitely want to keep track of variability. We're less worried about variability being either tight, low variability, high variability, medium variability, as long as the groups that we're comparing have similar variability. So the final thing I want to leave off on is a review of the type 1 and type 2 errors, again within this greater framework of hypotheses and how we're thinking of hypotheses. Again, the alternate hypothesis and the null hypothesis. So definitionally, a type 1 error is an error in hypothesis testing in which the null hypothesis is rejected when it's true. In other words, we have claimed the alternative hypothesis is supported and we found an effect, when in reality, that was not the case. A type 2 error is an error in hypothesis testing in which there is a failure to reject the null hypothesis when it is false. In other words, we claim there's no effect when there actually was. And these are the two types of errors that can occur. Now notice that because we've set our p-values, our alpha at 0.05, broadly speaking, we are, as a field, more worried about the type 1 error. We're only going to claim an effect when we're 95% sure. But by its very nature, that means we are increasing the chance of type 2 errors, that we're missing real effects because we're rejecting them because they weren't just quite strong enough in this particular sample or this particular study. And again, that brings us to this decision matrix that we have talked about in previous lectures. And again, the basic concept here is that we never truly know what reality is. We don't know if the null is true or false, but we can conclude it. And what we're hoping is that when we reject the null hypothesis, we accept the alternate hypothesis, it actually is true. The alternate is true, the null is false, and we're in the condition we refer to as power. the odds of saying there's an effect or gain when in fact there is one. What we're worried about is that type 1 and type 2 error. So type 2 error is when we reject the null, or accept the null, reject the alternative, and say there is no effect when there actually was one. Now again, we're never going to know for sure when we do this. The way we find this out, honestly, is over time as other people study the same effects, and we start to notice that people are finding statistically significant effects when we did not. This can also go in the other direction. We might find the type 1 error through time. We may actually make a type 1 error. We claim the alternative hypothesis is supported, we reject the null, we publish the paper, and as people try to replicate our study in different ways, they keep not finding that effect. That would start to be an indication that we may have made a type 1 error. So again, this is more of a theoretical or even philosophical way to think about hypothesis testing, because one half of this equation we never really know in reality. We can only estimate and make claims based on our hypotheses, our methodology, and our statistics. It's up to multiple studies over time to determine whether we're in a type 2 or type 1 error. And again, if we claim an effect and other people look for it and they find the effect too, we are probably in power. If we don't find an effect and other people do the study and they also don't find the effect, we're getting more and more likely we're just confident that there's no effect. However, if we claim there's no effect and then other people keep finding the effect, we probably post hoc, if you will, and post hoc means after the effect, probably start to recognize we likely made a type 2 error. And likewise, if we claim an effect and then everyone else that researches it afterwards can't find that effect, we have to start to accept the possibility that we basically fell prey to a type 1 error. So again, confidence level, type 1 error, type 2 error, and power are the 4 conditions we can end up in. We hope to end up in power, and we want to basically frame our hypotheses based on past theory. We want to create a powerful study using proper methodology, and we want to use the right statistics to look for this so that we can be as confident as we can that when we find an effect, we're certain that it's there. But just recognize we never know 100% for sure. So the main points, predicting no relationship or effect is a hypothesis, but it's often not the focus of research, and it's often not directly stated, but it's worthwhile asking yourself with each hypothesis, what is the null? It's a way to test to see if that hypothesis is a clean, clear hypothesis that's supportable or rejectable. Hypotheses that predict a relationship or effect need not specify the direction of the relationship, but often do, based on past theory and in an effort to create more power. And it's very important to use a research design and statistical procedure that's appropriate to the hypotheses. And that's really what we're going to be doing for the rest of this class, is we're now going to start talking about what are the different statistical procedures and when would we use them to test various hypotheses.